Hello everyone, welcome to our presentation about Chinese content scoring. In this work, we firstly present three short answer datasets for Chinese. Secondly, we adapt a state-of-the-art content scoring system and evaluate it in several settings on these datasets. Here is the overview of this presentation. After a brief introduction about automatic content scoring, we analyze the challenges of this task in Chinese in comparison to English. Prior work for Chinese content scoring shows a lack of open access data in the field. Therefore, we present three short answer datasets for Chinese. The Chinese Educational Short Answer Dataset, or in short CISA, ASAP-ZH, and ASAP-ZH Machine Translated. Our datasets as well as the experiment setting will be open released for reproduction. At last, we will discuss about the results and possible future work. In the area of automatic content scoring, we use natural language processing and machine learning technologies to score short answer questions automatically, which takes the correctness of content as the only metric. For example, if we have a question about the eating habits of pandas, the machine should tell us that the first answer is correct, while the second one is wrong. It sounds quite easy if we have enough training data with human annotation. However, the tricky part is that if an answer contains spelling errors, like the third one, it should also be scored as correct. Variance in learner answers like this has a major influence on content scoring performance. The more variance between the answers to a specific prompt, the harder it is to score automatically. In English and Chinese, this challenge manifests itself differently. Spelling errors in English can be classified into noun-word and real-word spelling errors. In our example, bamboo is a noun word, while beer is a real word spelling error. Both error types occur frequently in English short answer datasets. For Chinese, noun word spelling errors are rare and even impossible for digitized data because of the pinyin-based input method. After typing a pinyin, a writer is shown all corresponding characters from which they choose the right one. As this selection list contains only valid Chinese characters, non-word errors cannot occur by definition. This behavior generates two types of real-word spelling errors. In our example, spelling errors like confusing 穷 with 熊 are normally caused by wrong letters typed. The other error type is choosing a wrong word from the homophones. Leads to spelling errors like 珠子 instead of 竹子. Researchers found that nearly 95% of errors are due to the misuse of homophones. In order to reduce the influence of these errors in content scoring, introducing features presented as pinyin might be beneficial. Variance of linguistic expression is obviously found in both English and Chinese short answers. In English content scoring, lemmatization is often considered as a useful method to reduce part of the variance. In this process, words are reduced to their base forms, such as substituting ate with eat and deleting the s after bamboo. In Chinese, similar grammatical morphemes, such as le and men, termed as auxiliary words, which indicate the past tense and plural, can also be deleted in a pre-processing step to achieve a similar effect as lemmatization. Another type of variance is caused by synonyms. For such cases of lexical variance, external knowledge is often needed to decide that two different words are interchangeable. However, as we can see from our examples, some synonyms, such as panda bears versus pandas and 竹子 versus 竹, they share some characters. so such similarities can be covered by character features. Based on the main challenge of linguistic variance, there are also two special challenges in Chinese. Firstly, unlike English, which uses spaces as natural separators between words, segmentation of Chinese text into tokens is challenging. Furthermore, there are more options on which level to segment Chinese text. Apart from tokenization and segmentation into characters, which are two options also available and often used for English, segmentation into components, radicals, and even individual stalks are additional possible for Chinese. We review our prior work on Chinese content scoring and found out that there is no publicly available dataset, which becomes the major obstacle to reproducibility in the field. We also noticed that they all use lexical features on the word level, such as word engrams, which are mostly segmented by the Jieba tokenizer. In this case, we decided to collect and publish new datasets and test them with different feature sets on other segmentation levels. The first data we collected called Chinese Educational Short Answers, or in short, CISA. It contains 5 questions from the physics and computer science domain. Answers are collected from 360 students in the computer science department of Zhengzhou University. Each participant was required to answer each question with a maximum of 20 characters, resulting in an average answer length of 13.5 characters. 2 annotators speaking native Chinese with computer science background scored the answers into 3 classes, 0, 1, and 2 points. With an average inter-annotator agreement of 0.9 quadratically weighted kappa, or in short QWK. Here shows an example in CISA dataset. Prompt 5. The question is, what is machine learning? The second dataset we collected is based on ASAP short answer scoring dataset, which released by the Hewitt Foundation. ASAP contains 10 short answer prompts covering different subjects and about 2,000 students' answers per prompt. Prompt 1, 2, and 10 are science-related tasks, which do not have a strong cultural background and are therefore considered as appropriate to be transferred to other languages. Therefore, we collected answers in Chinese for these 3 prompts after manually translating the prompt material. The data collection provider Basic Finder helped us to collect 942 answers altogether, 314 answers for each prompt. They are collected from students in high school from grades 9 to 12, which is comparable with the set of English answers in the original ASAP dataset. The answers are transcribed into digital form manually after being collected in handwriting. 2 annotators speaking native Chinese scored the ASAP-ZH data with an average QWK of 0.7. Here shows an example in the ASAP-ZH dataset, prompt 10, about which color should be used to paint the doghouse and why. For comparison, we also translated the English answers in prompt 1, 2, and 10 in the original ASAP short answer scoring dataset to Chinese using the Google Translate API. The average length of translated answer is larger than the length of the original Chinese answer to the same prompt in our recollected dataset, aka ASAP-ZH. One explanation could be that the paid crowd workers are less motivated than actual students, and therefore read shorter answers. The example here shows that some translation errors can be found, especially when errors exist already in the original text. Words containing spelling errors are simply not translated at all. The word like coolest is wrongly translated into 最酷的 instead of the correct 最冷的. In our experiment, we applied the Escrito toolkit and extended with readers for Chinese text. Escrito uses a support vector machine classifier using the SMO algorithm. Due to the limited amount of data, we use tenfold cross-validation on both collected datasets. For all kinds of features, we use the top 10,000 most frequent uni to 5 grams. As a baseline, we follow previous work and use tokenization as segmentation. Then we segment data on character, components, radicals, and strokes level. In the last feature set on token level, we remove all the grammatical morphemes to reduce the influence of expression variance. As a result, we see that all feature sets were able to learn something meaningful from the training data. Although the performance of different feature sets is quite close to each other, we see a slight but significant advantage across datasets of component and character features over the token baseline. The usage of pinyin did not bring the expected benefit, possibly because the amount of spelling errors is not substantial enough in the data. Similarly, removing auxiliary words appears to have little influence on scoring performance. In the future, we will extend our comparison of segmentation levels also to a deep learning setting, using embeddings of different granularity. That's all from my presentation. Thank you for watching. If you have any questions, please contact us per email. Goodbye and have a nice day.